Welcome again for this NPTEL course on advanced reinforced concrete design. We are discussing the module 2, which is about material properties of concrete and steel. In the previous parts of this module, we talked about short-term properties of concrete and long-term properties of concrete. Now, in this lecture, we will talk about mechanical properties of reinforcement. Now, after attending or after this video, the student should be able to explain what are the different types of reinforcement bars used in reinforced concrete, and the student should also be able to discuss the advantages and disadvantages of steel and fiber reinforced polymer rebars, and they should be able to list different grades of bars that are available and explain the stress strain behavior of steel, and again explain the stress strain curve behavior of FRP rebars when it is used as a reinforcement. Right. The question is, why do we need reinforcement? We have discussed in the previous lectures as well. Plain concrete is weak in tension and it is strong in compression. So concrete cannot take tension. So the tensile strength is usually about 10 to 8 to 15 percentage, depending upon what tension that you're talking about. So it is weak in tension, right? So the plain concrete is usually used in structures where there is no tensile stress going to develop. Example, some flooring, some foundation bed, and etc. There also we need to provide, it's a good practice to provide some minimum reinforcement. But in most of the applications, concrete is used with reinforcement, mostly steel as a reinforcement, to tackle the tensile stresses that are coming from applied loads, right? And you can see several examples that are shown in the figure where we are using reinforcement to tackle different types of tensile stresses that develop. Right. So if you look at IS 456 2000, it permits using any of these listed steel types. The first one is a mild steel and medium tensile bars corresponding to IS 432, and it gives specifications for mild steel bars. They have two grades, grade 1 and 2, and also there are medium steel bars. Then high strength deformed steel bars, which conforms to grade A of IS 1786. We have now multiple grades that are available: FE415, FE415D, and FE500, FE500D, FE550, FE550D, and nowadays the market FE600 is also available. So now D, the letter D stands for, it should also for ductile design, so it has higher elongation at failure. We can also, for certain applications, we can also use hard drawn wire fabric, which conforming to IS 1566. These hard wire fabric, either it is usually, it is welded wire fabric. They are come as an oblong or rectangular mesh, or sometimes they are also available as a square mesh. And structural steel, as we know, I think we are not going to use it as a reinforcement. Maybe sometimes concrete filled, you can depending upon the requirement, some steel sections are also embedded in concrete also. But here in this lecture, we are going to talk about only reinforcement rebars that are embedded in concrete. And these rebars are available in variety of sizes. They are called as nominal sizes, which is a value that we actually use in our property calculations. If you measure it, it may be slightly lower or higher. Usually it should be, the measured property should be higher than the nominal sizes. So we have different sizes that are available: 4 mm, 5 mm, 6 mm, 25 mm, 28 mm, and so on. They're available up to 40 mm diameter. And the specifications are given in IS 1786 2008. In fact, other sizes also can be supplied by the manufacturer depending upon the scale of procurement. Now we have plain bars which were used in the olden days. However, the plain bar, they do not have these ribs. Okay, and they also have low strength of 250 megapascal as the yield strength. Now, this is one type of bar which were used in the past. Nowadays, they're not commonly used. These cold twisted bars, as you can see, the bars are twisted, and you can see this twisting also, right? So these are called as twisted bars. You can clearly see this kind of twisting is done to the bar to improve the mechanical properties. So these cold twisted bars are actually steel bars. Okay, reinforcement, they are processed through something called cold twisting process. They are twisted, and though they are called cold, actually some level of temperature up to 400 600 degrees centigrade, they are heated, and the temperature is kept below this recrystallization temperature for the steel. Okay, and this cold twisting process, usually what they do is they take a plain round steel bar and they twist it in a cold state. Again, it is not really in a cold temperature. There is a temperature is also applied, but the temperature is kept less than this recrystallization temperature, usually 400 to 600 degrees centigrade, using a specialized equipment. Okay, so what it does is when you do this twisting process, it creates a spiral pattern along the length of the bar. That is what we saw, resulting in a textured surface with raised ridges and depressions. That's what we have seen in this image that we are seeing here. Okay, you can see clearly the depressions and the ridges that are forming, right? This twisted pattern, what it does is it enhances the grip between the bar and the surrounding concrete, thereby helping to improve the bond. But what happens is during this twisting process, they also develop a lot of residual stresses. In that process, their corrosion resistance is also somewhat compromised. Okay, and these are actually high strength deformed bars, and their yield strength is expected to be 50% higher than mild steel bars. So you can see Fe415, Fe500, Fe550, all of them have 50% higher than the Fe250 yield strength, which we use for plain steel bars. And twisting can cause surface defects. This is one of the disadvantages, and because of the torsional stresses that you are inducing in the manufacturing process, and because of this, it also becomes less corrosion resistance. Okay, because you are putting some residual stresses during the manufacturing process. Nowadays, commonly what is available in the market are these are called thermomechanically treated bars, are also called as in short form TMT rebars. And what is this TMT process? Thermomechanical treatment is actually simultaneous application to steel of heating and cooling. Basically, what we do is we heat it and cool it suddenly over a very short period of time. So what that's what they call it as quenching. There are three essential steps that are involved in this manufacturing of the steel TMT rebars: quenching, self-tempering, and then atmospheric cooling. So what it does is these three processes, it helps to develop better properties in the steel by refining its microstructure. Okay, so when you do this heating and quench it, and then you do the self tempering, what you actually create is a tougher outer core. Okay, the red color that is shown in this figure, which is very tough, and then because you heat it up and you cool it, so basically the toughness of this outer core is going to be much better, and but the soft core, the inner core, is going to remain soft, and it is going to provide the required ductility. So the high strength and ductility comes from this TMT manufacturing process. So actually, during this quenching, self-tempering, and atmospheric cooling process, what happens is the steel turns into ferrite pearlite structure. So that means the outer core becomes very strong and the inside one remains soft. Okay. So you have multiple grades that are available in TMT rebars. One is this Fe415, Fe500, Fe500D, Fe550D, and Fe600. So again, D stands for ductile. So for seismic applications, sometimes we use this A50, Fe500D or Fe550D, depending upon the requirements. Right. And again, during the manufacturing process, these surface of the bar is also created with these ribs, okay, or sometimes they are also called as mechanical lugs. So different patterns can be created, okay, and these protrusions also should satisfy some minimum requirements. The idea is basically to transfer properly the bond uh, from concrete to steel and steel to concrete. So the bond between concrete and steel, adequate bond strength has to be ensured. So you have multiple these kind of patterns that are possible. You can see here different patterns, one like this, okay, and another like the spiral, double spiral, okay, and double spiral with a larger spacing. Of course, this double spiral, because you have these lugs in two directions, you have a better bond. Okay. So these kind of different types of surface preparation can be made into the surface of these steel rebars. Now let us look at this stress strain behavior of this steel of different grades, which are commonly that is available: Fe 250 and Fe 415 and Fe 500. And the number indicates 250 indicates its yield strength. And for mild steel, we know that the stress strain curve behavior remains elastic, right, up to a certain point, and we know that strength. So usually the elastic modulus is basically calculated from ES, can be calculated by basically Fy by Ey. So in a mild steel, actually, sorry, so this is epsilon y, right? So for a mild steel, uh, the yield is well pronounced. So you get the nice plastic portion. So you get upper yield, lower yield, and then you get this nice plastic portion. Then you get this strain hardening portion. So this the point of yielding is can be very well defined. So this is the characteristic of this mild steel. Okay. But when you go for Fe 415 and Fe 500, these are high strength steel bars. They do not exhibit this well defined yield plateau. Okay. So usually what we resort to is 0.2 percentage proofs thing, a strain. So you draw a strain at 0.2 percentage. You draw a parallel line corresponding to this initial elastic modulus, and wherever the curve touches, that is what we define that as the 0.2 percentage or yield stress. Right. Right. So if you go as you go higher in grades, of course your yield strength is increasing and your ultimate strength is also increasing. Similarly for Fe 500 also. So as the grade of steel increases, your yield strength increases and your ultimate strength also increases. Another important point to note here is mild steel. If you see here, the strain at failure, usually it is expected to be from 0.18 to zero point 0.2, or in other words the strain is ranges from 18 to 20%, which is a very very large strain if you look at it. And it really stretches like a rubber band, the steel. It can, if you take a 100 bar, uh, the length has to become 120 uh, before it actually fractures. Okay, there's a very large strain. That is why steel provides good amount of ductility for reinforced concrete system, and it gives enough warning um, uh, in design. So that is why steel is used as a preferred reinforcement with concrete. So again, ductility can be defined as basically a difference with as a ratio of, you can see if we define the yield as delta, okay, ductility as let's say delta or mu, we can define that as epsilon u divided by epsilon y, right? So different ways people define ductility, but it is measure of the plastic deformation, and it is able to hold the stress for a long range of strain without reduction in its stress capacity. So that helps. So one thing that to note here is as you go higher and higher in grade, as we have seen in concrete also, we go for high strength concrete, the ductility or the post peak deformation in the system is going to reduce. Same way for steel also, the ultimate strain, if you look at it, if for Fe415 it ranges from 0.014 compared to zero point 0.2 for Fe250. Similarly, if you go for Fe500, and it is basically it's about 0.012, or it's about uh, right. So about if you multiply by 100 in percentage, it is going to be 1.2 percentage, and this is about 0.016, right? So this is the strain. So the ultimate strain is going to reduce with increase in grade of steel. So that point we have to consider. Uh, so the higher the strength, the lesser will be the ductility that is offered by the steel. Now let us see for steel, what is the characteristic strength. So let's look at it again. Steel is manufactured in the factory. So the quality control is expected to be much better than concrete, which is usually for cast in place construction, which is made in the site. So gamma M for steel is actually taken as 1.15, which is lesser than 1.5 that is used for concrete. So if you see here, this is a characteristic curve. Again, characteristic strength is only 5% of the sample is expected to fail below that specified value. That is what we define that as a characteristic strength, right? So this is the characteristic curve. So for mild steel, if you look at Fe250, which exhibits a well-defined yield plateau, it yields at about Fy by Es. Fy is 250, 250. And elastic modulus for steel is 200 gigapascals. So if you substitute that, you get yield strain of about here. This is for design curve. For characteristic curve, when you look at it, it is going to be Fy by Es is your epsilon y. That works out to be 250 divided by 200 into 10 to the power of 3, right? So 200 into 10 to the power of 3, 200 or 200 gigapascal. So if you substitute that, you're going to get 0.00125 as your actual yield strain from characteristic curve. However, what we do is we knock it down the characteristic curve by partial safety factor, which is gamma m. So yield strength becomes Fy divided by 1.15. That works out to be 0.87 Fy. Similarly, your yield strain also is going to be slightly lesser, which is 0.87 Fy divided by Es. After that, but the one thing to note here compared to that of concrete is this partial safety factor is applied only from yielding, okay, or it is not applied at all the levels of stress, okay, because it is manufactured in factory. The quality control is expected to be better, so we don't reduce the stress strain curve at all levels, only close to the yield, and after yield we reduce the characteristic curve by partial safety factor. And this is the design, the stress strain curves that are specified for Fe415 steel. And this is your characteristic curve. Again, as we have seen for high strength steel rebars, the yielding is not well defined. So what we do is at 0.2 percentage, what we take is, this is the 0.2 percentage, and we take a parallel line and then we draw. So this is your initial slope. The same slope, you take it and draw a parallel line. Wherever this intersects, that is what you define that as your yield stress. Okay, because the yielding is not very well defined in high strength steel rebars, Fe415 or Fe500 or Fe550T. Right. So this is the way we define. This is 0.2 percentage. That's why 0.2 divided by 100 becomes 0.002, and you draw a parallel line with the same elastic modulus slope, and wherever it touches, that becomes your yield stress. Now if you see here, there are several dotted lines that are specified in this. Okay, those corresponds basically knocking down. So for example, the design curve, we start knocking down only for about 0.8 of your Fy. Then you have multiple these dashed lines that predicts at different strain levels that are specified in your code. So you can knock down and you can get your modified design stress strain curve like this. Okay, so this is the way we get. Again, for design purposes, if you look at it, my yielding is actually defined at this point. So that can be calculated as 0.002 plus this slope. which is what we are writing here, which is taken as basically this has to be plus point, not 2. So it's going to be 0.87 FI by ES, which is 200 gigapascal plus 0.002. So depending upon the grade of steel, my yielding, what I use it for design is also going to increase. Okay, higher the grade of steel, higher will be the minimum yield strain that I should satisfy in my design. And in design, we will talk about inflection and other things. We always want steel to yield first, okay, before concrete reaches its failure strength. So, because the steel has this nice ductility, where if the steel is yielding first, it is going to give you a lot of warning before concrete reaches its ultimate strength. So, this is your yield strength from design point of view. Okay, again, you can calculate that. Right, same way you can do that for FE 500 as well. Okay, now so if you note down again characteristics, partial safety factor gamma c which we apply for concrete, it is applicable for all the stress levels. Okay, we knock down the stress strain curve by applying this gamma factor for all the stress levels. But in case of reinforcing steel, the partial safety factor gamma is applicable only for the inelastic region. It is not really applicable for elastic region. Another thing that you should also note down here is the elastic modulus for steel is not really function of your yield strength. Whether you take Fe 250, Fe 415, or Fe 500, or Fe 550, elastic modulus is going to remain nearly same. Is going to be 200 gigapascal. All right, and if you go for pre-stressing steel, you will get slightly lower reduction for high strength steel. That is also, in fact, will be very close to that of 200. Usually, it is about 190 to 200 gigapascal. Okay, right. So for concrete, again, the stress strain curve is directly affected by changes in the compressive strength of concrete. However, here, though the grade of steel changes, the elastic modulus doesn't really change. Right. Now let us briefly talk about how the Indian Road Congress gives specifications for different types of steel that can be used as reinforcement. So IRC 112 allows you to use hot rolled steel, thermomechanical or heat treated rods, or decoiled rods, or cold worked steel. All of them are actually allowed as per IRC 112. Again, they are allowing different grades of steel like Fe 250, like what we have it in IS 456, Fe 250, Fe 415, Fe 415D, Fe 500, Fe 500D, and so on. Now, the steel may be coated or they can be galvanized for improving its resistance to corrosion. In fact, there are special type of steel that are also available, corrosion resistant steel, CRS they call it. Uh, but the mechanical properties doesn't change. But during the manufacturing process, the alloy composition is changed to give better corrosion resistance. And you can look at specialized literature if you want to know more details about CRS, which is corrosion resistant steel. So as you can see here, different grades of steel are allowed by this IRC 112, Fe415, Fe415D, Fe500, and so on. And all these grades again of steel, they have to follow this specifications, which is IS 1786. For mild steel, it is IS 432. Okay, and these are the minimum yield stress that has to be specified. Again, the number indicates the minimum yield stress they should satisfy. Okay, for Fe 415, they should satisfy at least a minimum yield strength of 415. Fe 500, again, it should have minimum yield strength of 500. Now, what is this minimum tensile strength that they should satisfy? For Fe 250 grade, they should have at least 410 megapascal of ultimate strength. Okay, and for high strength steel deformed bars, the code is saying that it should be 110 percentage of your 415. Okay, or it should not be less than 485 megapascal. So if you see here, it is the minimum tensile strength as percentage of actual 0.2 percentage proof stress. That means the yield corresponding to 0.2 percentage of your strength, 0.2 percentage proof stress. That should satisfy minimum 100 percentage of what stress that you are getting at 0.2 percentage proof stress. Okay. So these are the minimum values that are given. Again, minimum elongation at failure is also specified. So you see mild steel, it has to have at least 23%. So that is the advantage with mild steel. You get a very high elongation until failure. As the grade of steel is increasing, as you can see here, okay, your failure strain actually is actually reducing. Okay, as we have seen, the more and more you use high strength material, you are going to lose ductility. For example, for APC 600, you get only about 10 percentage of elongation at failure. For example, when you look at it, for mild steel we get almost 23%. Okay, so these things that you have to keep in mind. Okay, right. And for seismic zones 3, 4, and 5, the code is saying that high strength steel should have a minimum elongation of 14.5%. So if you're using steel in seismic zones 3, 4, and 5, you should have minimum elongation to satisfy the ductility requirements. Because for earthquake design, we need to dissipate the energy that is induced into the system. So yielding is one way where you can really dissipate a lot of energy. That's why the steel rebars for seismic application, they should satisfy some minimum elongation. Right. Now let's look at how the design stress strain curve that are specified for steel rebars. We are plotting stress and strain, and you look at it is compared to this IS code, which gives different dashed lines and all. It gives a very simplified bilinear curve. Okay, elastic portion stays still till Fy, and then you get this bilinear curve for this characteristic curve. Then that characteristic curve, again you divide it by partial safety factor, which is gamma s is 1.15 for steel. Then you get this design curve. Okay, and it is also satisfying some epsilon u values. The values that are given in the table that we looked at it. And ultimate strain for design, we take a slightly lower value of 90% of your characteristic strain at failure. So that is what we use for design calculations. It's a very simple bilinear curve. Okay. And sometimes if you want to do a quick calculations, you can ignore this hardening portion and you can make it like a elastic perfectly plastic relationship also. Because then in that way, whatever that extra strength that is given by the steel, you are ignoring your calculations. So you're going to conservatively estimate the capacity. So that is why the code is also allowing you to use this simplified elastic perfectly plastic curves also in your design calculations. Now, so this is with respect to steel. Now, we should also look at what are the disadvantages of steel as a reinforcement. It gives very good ductility. It has an excellent compatibility with concrete because the coefficient of thermal expansion is nearly same as that of concrete. So you're not going to have any residual stresses. But there is one major problem that we find with steel as a reinforcement is they are very susceptible to corrosion, especially when the steel, if it is exposed to chlorides and sulfates and oxygen and moisture, the corrosion, the pH level of uh, passive film on this rebar is going to go away when the pH is reducing to the level of 10 or so. Then the corrosion starts. The problem, the moment the corrosion starts, you form these iron oxides, which are basically having larger volume, and that is going to put lot of pressure on the surrounding concrete. Then the concrete around this bar is going to crack and it is going to spall away. The moment this process starts, then your durability of the structure will be compromised unless you do some necessary intervention. So this is the problem when we use steel as a reinforcement. And now we can tackle the corrosion by multiple ways. Okay. The major effect of corrosion is the reduction in strength and stability, and it can lead to catastrophic failure. The ductility associated with steel can be lost, and it can lead to catastrophic failure. The solution to address this corrosion is either through galvanization or some kind of resin coating that we can apply, like this epoxy coated steel rebar. But some research is showing that if you're not careful while you handle this epoxy coated or coated rebars, then in fact it can aggravate the corrosion. So you can lose this coating in a localized way, and it can induce this localized corrosion or pitting corrosion. So this is also not a good solution if these coated rebars are not handled properly. So one thing is, what are the alternatives that are available for steel as a reinforcement? One is, nowadays for some applications, these fiber reinforced polymer based rebars are explored and being used, especially in the European countries and in North America, for various applications as an internal reinforcement. Now, what is this fiber reinforced polymer? FRP stands for fiber reinforced polymer. They are basically composite material, just like the concrete. We make it with different material to form a, solid material. Here also we make this fiber reinforced polymer using high strength fibers, which are embedded in polymer matrix, which are there also called as resin. Okay, and the fibers are the main load bearing elements, and this polymer matrix or resin helps to protect the fibers and keep them in place. And the main advantage with them is they are corrosion resistance. They are very lightweight, and so they give very high strength to weight ratio, and they also have this nice property of electromagnetic neutrality. So for example, if you want to make slabs that are going to hold this MRI kind of equipment, then this electromagnetic neutrality is a very desirable property. So such kind of slabs can be reinforced with this material. So usually these bars are manufactured using this process called pultrusion process. Okay. Now, different types of these FRP bars are available. We have glass FRP, which we call that as GFRP rebars, and we have carbon FRP with carbon fibers as the fibers. And if basalt fibers are used, these bars are called as BFRP bars. Sometimes aramid fibers are also used. They are called as AFRP or aramid fiber reinforced polymer rebars. And CFRP rebars have very high tensile strength and elastic modulus. In fact, elastic modulus you can get as close to that of steel. Sometimes, if you use high modulus fibers, you can get higher elastic modulus than steel also. However, they're very costly. So again, civil engineering applications are very cost sensitive. So they are not really used unless it is for pre-stressing applications. Nowadays, people are exploring CFRP strand for pre-stressing applications. However, these glass FRP rebars are very economical compared to that of other FRPs. So they are very commonly used as an internal reinforcement. Now let us briefly look at what are the mechanical properties, like what we have seen for steel, how these mechanical properties are going to change for different types of FRP rebars. And you see here, I have shown only strain up to 4% here, right? So if you look at the stress strain curve up to this, if I'm comparing, let's say this 415 steel, this is the red color is your 415 curve, that I've idealized this as a elastic plastic response just to compare the behavior. And if you see that the elastic modulus for steel is 200 gigapascal, but for glass, you actually end up with from 40 to 60 gigapascal. So that is one of the disadvantages with this material. It has low elastic modulus. But if you're using carbon, you can get as close as possible to that of steel, or sometimes it can even lead to higher elastic modulus. Another thing to note down here is these bars, they exhibit linear elastic behavior. Okay, and as soon as it reaches its ultimate strength or ultimate strain, it is going to rupture and it is going to fail without giving any warning. And steel, we know that it is a very nice material. After yielding, it is going to sustain large strain and at the same stress level, and they may also exhibit strain hardening, and it is not going to fail even after failing, even after yielding, and it is going to fail at a very large ultimate strain. But if you see here, the strain at failure for this FRP, GFRP bars are also around 2.5% compared to that of 14 or 15% that what we get for high strength steel rebars. So this is one of the disadvantages. Elastic modulus is low. The strain at failure is also going to be low compared to that of ultimate strain of failure for what we get for steel. So steel exhibits ductile failure. It has a very high elastic modulus of 200 gigapascal. However, FRP exhibits lower elastic modulus. However, if you look at FRP has strength of, even for glass, we get a strength in the order of 1000 megapascal, which is a they have very high strength. Only thing is their elastic modulus is low, and they are also exhibit linear behavior, and they are, when they fail, it is going to be brittle in nature. Right. So these bars are now used for variety of applications which are sensitive to corrosion. Okay. However, you have to tackle the ductility aspects by other means. Okay. So in summary, in this lecture, we talked about different types of steel reinforcement used in reinforced concrete. We also talked about the stress strain relationship for different grades of steel, and We compared how the sustained curve behavior for steel is given in IS 456 and IRC 112. And we also briefly talked about what are the disadvantages of steel. The main disadvantage is the corrosion related with steel, and one of the alternative solution is possibility of using this fiber reinforced polymer rebar. And we also talked about how the stress strain curve behavior of FRP rebar and the stress strain characteristics of this bar also we discussed. So this is the summary of today's lecture. And with this, we will end this module 2. In the coming weeks, we will talk about durability aspects of reinforced concrete. Okay, thank you. And these are some of the references.